Greenhouse warming theory is rapidly becoming the most expensive mistake ever made in the history of science. Video 13. Where did this revolution in science come from? In 2006, as explained in Video 5, I stumbled on detailed data on the internet from ice cores drilled under Summit, Greenland, showing that the greatest volcanism recorded in Greenland ice was contemporaneous with the greatest warming at the end of the last ice age. This did not make sense. Large explosive volcanic eruptions are well known to cause cooling. How could volcanic eruptions also cause warming? Having studied volcanoes all my life, I became fascinated and ultimately consumed by the quest for new understanding. I had a clear instinct that figuring this enigma out could be very important. Being retired and self-funded, I was able to follow the data wherever they led without concern for time, funding, promotions, office dynamics, committee meetings, writing proposals, or the need to defend any existing theories concerning climate change. My only concern was to satisfy my own curiosity, doing the best science I could, just trying to understand what is happening physically in the world around us. I soon put aside nearly everything else in my life, concentrating full-time on many different disciplines, including climate science, atmospheric chemistry, radiation physics, volcanology, and paleoclimatology. Consulting more than 10,000 papers, shelves of books, and hundreds of websites over 13 years. Perhaps most valuable, I could just let things simmer, becoming comfortable with a whole lot of unknowns. There was no need to jump to conclusions because there were no deadlines. I had the chance to explore conflicting views and to regularly question my own emerging views, especially as they began to diverge from majority views. I am a rather pragmatic field geophysicist who believes firmly that physics is about what is physically happening in the world around us. If our explanation of a physical process is not physically intuitive, our explanation is not physics, it is mathematics, or else we need to improve our physical intuition. It takes good mathematics to do good physics, but you can do outstanding mathematics without any regard for physics. I understand clearly the value of mathematical equations, but I see them as tools, not as conclusions. Most equations are built on a suite of simplifying assumptions that must always be remembered. We often must make assumptions in science in order to move forward. The trick is to remember what is an assumption and what is a direct observation. In science, we typically make observations of something that has happened or is happening, and then try to determine the cause. There are typically many possible causes that can be described by many different systems of mathematical equations. The problem is to determine the actual cause, which may or may not be included in the causes we are considering. I have also come to realize, like many other scientists, that the more complicated the explanation, the less chance it describes accurately what is actually happening physically in nature. If there is a lot of arm waving going on, be suspicious. The essence of human beings is not their ability to reason, but their ability to rationalize. There's a lot of rationalizing, motivated reasoning, and arm waving going on these days over greenhouse gases, temperature trends, and tuning climate models to fit data. As I dug deeper, things started to unravel. Over the years, I've asked myself many fundamental questions. What holds matter together? Are these bonds rigid? What is thermal energy in matter? What is temperature in matter? What is temperature in air? What is temperature in space? How does thermal energy radiate spontaneously? What is thermal radiation? How does radiation travel? Radiation cannot physically travel in space as waves because waves are the deformation of matter and there is no matter in space. Electromagnetic radiation is well observed to be a continuum of frequencies of oscillation covering more than 20 orders of magnitude from radio signals to gamma rays. How could a continuum travel as photons? Is there a different photon for every decimal place? What happens physically when a photon of light interacts with a molecule of gas? How and why are spectral lines of absorption formed? What physically are an electric field, a magnetic field, and an electromagnetic field? What physically is resonance? How does resonance work? How do life forms sense and interact the world around them? How do we see, hear, taste, smell? How does solar energy interact with Earth's atmosphere? What warms the stratosphere? What forms the ionosphere? What forms the ozone layer? What frequencies of solar radiation are absorbed in the upper atmosphere, and why? How do ozone concentrations vary through time, latitude, and region? There were new questions every day. Some of them took years to answer, others still have not yet been answered adequately. I was impressed how many of these fundamental questions had not been addressed adequately in the scientific literature. Many were described by mathematical equations that many times just did not feel right to me. The confusion over waves and wavelengths was and still is widespread. We cannot see radiation. Why do we insist in explaining something we cannot see in terms of things we can see or at least visualize, such as waves and particles? Wave frequency equals the velocity of light divided by wavelength. But frequency of oscillation is something very different from wave frequency. Greenhouse warming theory is built on the assumption that greenhouse gases absorbing infrared thermal energy get warmer, or somehow warm Earth. But less than 16% of the frequencies making up terrestrial energy are absorbed into the bonds of the trace amounts of greenhouse gas molecules, which has essentially zero effect on the temperature of a gas. Angstrom showed this in 1900. This assumption of greenhouse warming has never been validated by experiment, a cornerstone of the scientific method. I did an experiment in 2017, as explained in video 7, that measured no difference in the temperature of air containing more than 23 times normal concentrations of carbon dioxide. Climate scientists and climate models calculate that there is a greater amount of infrared energy than ultraviolet B radiation. This led me to realize that heat is not about amount. It is about the difference in temperature between the source and the absorber. Furthermore, we know that ultraviolet B radiation has about 50 times the energy of infrared radiation absorbed most strongly by carbon dioxide, no matter the amount. Radiant energy is a function of a broad spectrum of frequencies, not a single amount of watts per square meter. Current ways of calculating heat work reasonably well for systems with similar temperatures, but they fail catastrophically in climate calculations, where sun is 20 times hotter than Earth. Physicists in the late 19th century and still today think of the brightness or intensity of radiation as the energy. Therefore, Planck's law, as originally formulated, plots energy as a function of wavelength. Yet Planck postulated, when writing out his law, that radiant energy is equal to the frequency times the Planck constant. He saw this as a neat mathematical trick and never thought about the fact that if energy is a function of frequency, energy must be plotted on the x-axis, the same axis as frequency or wavelength. Planck's law stood out as an experimental triumph relating temperature to a broad spectrum of frequencies, but Planck and experimental physicists in the late 19th century were confused between energy and intensity or amplitude of oscillation. Physicists thought they were measuring energy when they were actually measuring amplitude of oscillation, which we perceive as brightness or intensity. In many ways, my primary contribution to physics is to bring improved understanding to the Planck-Einstein relation and to Planck's law. This has major implications for climate change, for quantum physics, for particle physics, and for identifying a theory of everything. These 13 years have been incredibly stimulating as I work systematically through many, many issues, just trying to explain observations of nature. I was surprised to find that very few physicists have actually thought critically about the physics of greenhouse warming theory. Having the time and the space to wonder and having the insatiable curiosity has helped me understand and experience what Planck said in 1936. New scientific ideas never spring from a communal body, however organized, but rather from the head of an individually inspired researcher who struggles with his problems in lonely thought and unites all his thought on one single point, which is his whole world for the moment. Thank you.